Okay, Assalamualaikum and good morning. Welcome back. So today we'll continue with the lectures, beginning with a new chapter of the book. Let me just go to the book. So we are entering chapter 2. Okay, which is going to be still on thermodynamics. Essentially, we introduce entropy. So let's just begin. I've not uploaded my lecture notes yet because they are incomplete. So, and perhaps today, let's see how far I can go. Okay. So this is lecture 3. Essentially, we'll talk about second law of thermodynamics together with entropy, and we're going to introduce the idea of a heat engine, and we'll try to do more things from there. Okay, first and foremost, let's just recall for the reverse process. Just check if the auto admit is on. So if you recall the reversible process, we have this first law of thermodynamics, essentially giving you energy conservation. Let me just take my pen for the third. Okay, so this is for reversible process, you have energy conservation. Otherwise, you probably have an inequality there. Okay, so one of the things that we have looked at previously is the idea of this so-called cross T, which is really saying that this is not really a differential, but it's an inexact differential. Okay, so in other words, when you integrate this, you will see that this particular integral will depend on the path. Okay, so you remember we did something like this. Okay, and then we say that okay, the path underneath actually it's not that. We draw this properly. Everyone is in here. Okay. So you the process. So you have an isotherm here, and then we allow another process in such a way that there's this area enclosed thing. So this is isotherm, and no, essentially for this process to occur, this is not really what you call. It doesn't give you a reversible process. Okay, so in other words, what you have some inequality coming into this equation. Okay, you can refer to the notes earlier. So so in other words, it's not an exact differential. Okay, so but we have learned in maths method, for example, that differentials generally, which are not exact, okay, can be transformed into an exact ones by use of what we call the integrating factor. So you probably have think of this before, like this d of f equals to a of some function over here. This would be, let's say this is of y and z, like the one below. This would be d, just follow the one downstairs, and then this is b y z as a function of y and z. Okay, you can convert this to an exact differential by multiplying the whole equation by what we call the integrating factor. Okay, so if you can't remember this technique, you might want to look it up in your old maths methods notes. Here I just proceed with the example that is given in the book. So given in an inexact differential dx, so x here is thought as a function of y and z over here, and then this is given in terms of some function times dy plus some function times dz, where those functions are just defined like above previously, your a and b. Okay, so the a is z cubed, b is 2z plus yz squared. Now one could refer to the maths method notes what is the right integrating factor. Okay, so there is a technique introduced there, but over here the integrating factor is just simply an exponential of yz. Okay, so one actually multiply the whole equation with this factor, so you get exponent yz times dx equals to z cubed, which is coming from there, times exponent yz dy plus this whole thing times exponent yz dz. And this whole thing, if one can actually see what's happening over here, oops, I think that's a mistake. Let me check with the book. My eyes. Okay. So it seems I just followed the book. So yeah, okay. So this one, if you just look at it, let's work backwards. So if you take the differential of that, so you get 2z dz. Okay, you differentiate that, and then you differentiate the other one, and over here there are two variables. So the one with if you differentiate with respect to z of the exponential, you get the same thing but with a y in front, so you get yz squared. And if we differentiate your y instead, then you will get your z cubed, sorry, z cubed, right? So you get back to this form, but now you can actually write this as d of something, which is really the definition of your exact differential. Okay, so in other words, by doing this, one can now integrate this equation. Okay, so now the question is, does this method work for the case of the inexact differential of the case of this heat, okay, in this reversible process? Okay. Let's try to do this. And what do we do? Again, we'll do this in the case of a part, since we need to know the expressions of each individual terms. For example, u and p and v, we need something, some exact, some specific expression for those. So we'll work out this in the case of the simplest case that we have already have seen before, which is the ideal gas, and we take it to be the monatomic gas. Okay, so then when you do this, then you know what your internal energy is. So you'll be your number of degrees of freedom times the number of moles times R, the gas constant, times half theta G. Okay, so your 3 here is coming from the 3 degrees of freedom. So if one wants to have the differential of u, like the one you need above, okay, then this just simply gives you 3nr d theta G, because your n is a given constant and R is your gas constant, and the rest is just numbers. Okay. The other part, we need PDV, okay, which is you can think of this as a mechanical work. Okay, then you really have the equation of state that relates between PV and theta here. Theta is your gas temperature, and one can multiply P with dV and divide by V, and essentially we get that. Okay, so putting all this together into the equation, we have this what you call thing on the right, okay, which you can see that, okay, I need to make it integrated in some way. So what do? I will just, over here you can see there are two state variables, V and theta here, and over here is just theta. So I can simply remove this theta here, okay, by just dividing the whole equation by theta. Then a function of theta over here, and then a function of V over here. Okay, so let's do that. We divide by theta, gas temperature, and then essentially this is a function of theta there, and this is a function of V there, and you can integrate both, and essentially that gives you a log. Okay, so let's consider the integration is coming from some initial configuration to some final configuration, I and F here. So there will be, in this particular case, we look at the temperature. So there will be a temperature at the initial configuration, and then the final configuration, theta GF. Similarly for the case of the volume. So in other words, what we have over here is a function that depends only on the initial and final temperatures in this term, and then this is a function of the final volume and initial volume. I could put them together if I want to. That would actually gives you NR, and then I will have log of theta GF divided by theta GI to power of 3 over 2. The whole thing, it's not divided. Let me do this again. So I will have something like this. So let me just, I need more space in over here, but never mind. Let's see if I can fit everything in. Log of, what was it again? Yeah, your theta GF, theta GI, 3 over 2, and then the plus, you can combine these two logs together, and it will be a multiplication. Then it will be VF times VI. So over here, you can see that this is just some function of what? Theta GF, theta GI, VF, and VI. So it only depends on the final configuration and your initial configuration. Okay, so in other words, that tells us, okay, the whole thing will be independent of path because it just depends on the endpoints. So in other words, this whole new integral, so this thing is really a function of state. Okay, I should say that this one. Okay, so when you integrate, it only gives you something that depends on the endpoints rather than the path. Okay, so what is this thing? Well, this thing is essentially called entropy. Okay, if I write this thing as that, This S is now is what we call entropy. Okay. So let's just apply back this idea. When you integrate that differential, okay, so you get these two parts, okay, and then there will be some initial value of the entropy. Because why? When you put when you take S at theta naught G and V, then I think this is F, sorry, I was trying to do this in a rush. Oh no, it doesn't matter. Okay. So I'm making it, so I take theta G to be theta naught G and V to be V naught, okay, without the S naught, okay, this would be just 1, okay, so log 1 is 0, so but then, okay, you have 0 entropy. That's not quite right. You'll see that this actually doesn't quite fit with the third law of thermodynamics, so we need to give the initial condition of the entropy, which is now given in terms of this quantity S naught. Okay. Now, right. At this stage, what we have seen now is essentially your inexact differential referring to heat previously has been converted to a exact differential by multiplying an inverse temperature, 1 over theta. Okay, so your 1 over theta is your integrating factor in that particular case. But as yet, your temperature, you remember, there are various ways for you to, how should I say, various ways to define your temperature. Okay, so we have not made temperature as something which is well defined in some sense. So over here, the fact that this is going to be related to entropy, then one could actually give you a precise definition of the temperature scale, which is now known as what we call the absolute temperature. Okay, so this probably you heard about the Kelvin case. Okay. So this will actually coincide with the Kelvin scale of Kelvin temperature scale. Okay. Now, in order for us to define this idea of absolute temperature using this idea of entropy, one needs to do a little bit more work. Okay, one could accept it, but I think I will just follow the logic of the book. So it tells you about what are the intermediate steps before you can actually do this. Okay. The first step is to restate the second law of thermodynamics. Previously, we stated in this particular form. I think, where was it? Did I not mention it before? Oh, not yet. Okay. So we need to restate second law of thermodynamics, but in a way that is relevant to a heat engine, because we'll talk about heat engines after this. Okay, and we need to relate with what is known as the second law of thermodynamics in that context. And then we'll look at a particular heat engine called Carnot Engine. And this Carnot Engine is the most efficient engine that operates between two heat surroundings, or what we call heat bath. We will define this more probably after this. And then the temperature scale that we define from the ratio of heat flow in one cycle of Carnot engine will be the one that relates to the absolute temperature. Okay, and then the other things, no, the scale itself will be related to how you subdivide your Carnot cycles, and then finally we'll, we'll define the functional state called entropy using that so-called exact differential. Okay. So now we come to the point of defining your second law of thermodynamics. Again, there are various versions of this. So when you read different books, it might give you a different statements of the second law. Probably the most common one you have learned is what? Maybe I should now give some room for interaction. Can somebody state what is known as a second law previously? What you have learned? Anyone? Are you there? Okay. Can someone, one of you, define what second law that you have learned in probably in modern physics or thermodynamics? I'm not sure where you have learned this before. What second law of thermodynamics? You've done thermodynamics, right? Nobody wants to try? Nobody? Really? Okay. Perhaps this is Monday morning. Perhaps the most common that people heard about second law is the idea of entropy never decreases. Right? Is that what you have learned? It's awkward. So nobody has learned anything. Somebody has left the meeting. You have not taken thermodynamics. Oh gosh. Uh, what about modern physics? Do they treat thermodynamics? No, it's good that you tell me this because otherwise I wouldn't know. I thought you have done it somewhere. Or at least in mental class C or sixth form, you're taking. Okay. So what do you understand of your second law? Just checking.
It will increase until the system reach equilibrium.
Okay. So in other words, again, that is what I expect. So you only learn in the context of the entropy doesn't entropy always increases, right? So historically it doesn't work that way because no, they learn about energy and things like that before that, okay, and entropy comes much more in the context of the heat engine. So so in other words, there will be two statements of the second law that you probably have not seen then, okay, and after that, then it sort of got revised into a much more modern form where you talk about law. Second, sorry, your entropy doesn't decrease, okay. So let's start considering two systems which are placed in a thermal contact. So in other words, they will evolve. Let's say they might have different temperatures, and then they will evolve and then be in equilibrium to a new state. So they reach a new equilibrium state, and usually depending on how the state of this system changes. But the natural behavior, as you see, is that the, the evolution of the systems tend to be irreversible. It's only in very special contexts where you mostly are done in a much infinitesimal way of doing things, then you can do a reversible process kind of thing. Okay, but when you do two systems together and then live to equilibrate, usually that two system won't go back to the original state of the two separate systems. So in other words, there is irreversible behavior there, and that irreversible behavior tells about the preferred direction of how thermal system behave. Okay, so the other thing that one needs from this is the fact that you can define temperature, which is associated with the hotness of the body. Okay, and you observe that the heat actually flows from a hot body to a cold one. Okay, again, this is a manifestation of the second law. So you can restate your second law in that sense, but no, there are some conditions, of course, that this will be a natural evolution. So the natural evolution is that your heat will flow from a hot body to a cold body. It's not the other way around. There was probably an old idea. Let me just Google it. If I'm just trying to make sure I got the name right. There's an old idea that in the beginning people think of what we call the heat is actually going the reverse direction. Okay, so they talk about what I think it's phlogiston. See, is there some Wikipedia for this? Yeah. So in the old days, before they understand this properly, is that there is okay. They mentions here the fire-like element is called phlogiston. So it goes something goes from a cold environment to the body that gets hot. Okay, so then that element is what we call the phlogiston. Okay, so that idea is actually wrong, and of course today we understand much better. And in fact, statistical mechanics allows you to understand why heat flows from hot body to a cold body. Okay, so so that is a way of understanding second law of thermodynamics, saying that heat flows naturally from a hot body. You can force it to flow differently, of course. Heat flows naturally from a hot body to a cold body. Okay, so the other thing that we need when we want to discuss about engines is to talk about thermal reservoir. You can think of your thermal reservoir, or another word for it is what we call heat bath, is that the engine is going to be operating in some environment. Okay, and that environment is the where you release your heat or you absorb your heat. Okay, so a thermal reservoir is a body that has a huge heat capacity, so that, in other words, if you input energy into that environment, okay, into that system, into that thermal reservoir, okay, the temperature of the environment or the reservoir will not change. Okay, because the heat capacity is huge. Okay, so it can contain more energy, absorb more energy. Okay, so what else? Okay, now then, after having all these ideas, okay, about the idea of heat flowing from a hot body to a cold body, and then you have the idea of thermal reservoir, then we can actually talk about heat engines. Okay. Now, the first statement of the second law in the context of a heat engine is given by Kelvin and Planck. Okay. And it states something like this: it's impossible for an engine to operate in a cycle to take heat from a single reservoir and totally convert it to to work. Okay, that means there is no wastage. Okay, so it's impossible to do. Okay, and you have to remember that this second law was formulated during the industrial revolution. So when people talk about engines, so that's why it's been formulated that way. And then I think if I'm not mistaken, it's later Clausius made a different statement. It says it's impossible to construct a machine which operates in a cycle that produces no other effect than to transfer heat from a colder body to a hotter body. So there must, in other words, if you want to do that, there must be some other effect, which is actually work. Okay. So the important thing that one needs to what you call see in these statements is that your engine is operating in a cycle, machine which operates in a cycle. Okay. One could, if you remove this condition of operating in a cycle, okay, one could actually transfer heat from a colder body to a hotter body. Okay, so an example is given by this thing, which is also in the book. You place a gas in a cylinder, make contact with a cold reservoir, and then you expand the gas. That means when you expand the gas, it has to expanding the gas will lower the temperature. In other words, okay. So in other words, in order to be in equilibrium, then it has to take heat from the reservoir. Okay, so it's taking heat from the reservoir, which is the cold reservoir in the beginning, and then you remove the cylinder of gas from the cold reservoir and then put it in a different reservoir, which is hotter reservoir, and compress the gas. So when you compress the gas, then you actually increase the temperature, and then in order to be in equilibrium with the hotter reservoir, then you allow energy to flow into the hotter reservoir. But you can see that there is a cycle is, remember, a cycle is something that goes from one condition and then back to the original condition. And this is not quite so. So in other words, this process is not cyclical. Oops. Oh dear. Start to move not function. Let me just see. Okay. I will have to remove this again. Okay. Then let's see. It should work. Okay. Right. So now we talk about this so-called Canon engines. Okay. So the idea is the idea of an engine. What does it do? It takes a heat from some hot reservoir and then use this, okay, to convert it to some work, just like your steam engine, for example. Okay, convert the thermal energy into some useful work, and then but you cannot convert it totally, so there will be some remaining thermal energy get transferred somewhere else, and usually this is transferred to a colder thermal reservoir. So that's essentially the idea of an engine. Okay, so in this process, in order to make this particular cycle, one could use some ideal processes for which you know how to analyze them properly. So the first process would be an isothermal change. So with respect to work, with respect to process within a gas, for example, you can talk about pressure and volume changes. Okay, and these pressure and volume changes are made at a constant temperature. So in other words, this will involve isotherms. Okay, so like this over here, we'll talk about this in a minute. And then we have another type of process, an ideal process called the adiabatic change, for which your volume and pressure changes, but there's no heat entering the system. And of course, if your volume and pressure change, of course, you allow your temperature to change as well, to differentiate with the case of isothermal change. Okay. So in this process, really the system is actually is either doing work or work is done on the system itself. Okay. So we will make this into a cycle, which is shown in this picture over here. So over here you have this process. It takes up. So what's happening over here? You have this volume gets to be expanded, okay, to another volume, V2, for example, over here. Okay, it expands over here, and then to maintain it to be at a constant temperature, some heat will be taken up from some reservoir. Okay, so and then this is what we call an isothermal expansion. Okay, because otherwise, if you have expansion over here, then you actually cool down the gas. Okay, but then it takes up heat from some reservoir and it maintains at a constant temperature. And then you allow it to do another expansion. So it goes to a bigger volume here at C, but you don't allow any heat to come in. Okay, so it's just a natural evolution of your pressure and volume, pressure being decreased and your volume being increased, okay, without heat input. And the next one, so let me just go to the statement here. You can imagine the picture that you have before. So you go to compression. So the compression is going from this volume C here to volume D. Okay, so in other words, this goes from a large volume to a smaller volume, so it gets compressed. So when usually you compress a gas, the thing gets hotter, but in order to maintain a constant temperature, you release the heat from the gas to an environment. Okay, well, it's not in this picture, of course, but in other words, the idea is there's a heat loss coming in. Okay, and then final one is the adiabatic compression. It goes from this volume to this volume, or this pressure to this pressure. Okay, so putting all these processes together, then you have the full cycle. Okay, remember that your internal energy is because it goes into a cycle, your internal energy from the initial state to the final state doesn't change. But what's involved is the heat taken in here from some hot reservoir, and then the heat release from the body, from the system to another reservoir. Okay, so essentially that's why you have this inexact differential of the heat coming in to sort of balance up the relation of the first law. Okay, so so in this process, one aspect, this is the working of the what we call a Carnot engine. Okay, so what happens over here, there will be useful work being done in the midst of this cycle. Okay, so in other words, useful work is actually converted from the heat energy from the first reservoir. Okay, so there, how much work can be done is given by the difference between the two heat, the first heat being absorbed and then the second heat being released. Okay, and the efficiency of the heat engine in this particular case would be the ratio of the work output. Okay, so another this expression of work per cycle to the heat input. In this case would be Q1. So it will be W over Q1, or if you put in the expression for W from here, so you get Q1 over Q1 minus Q2 over Q1, so you get 1 minus Q2 over Q1. Okay, so a good engine will convert everything, all the heat into work. Okay, so in other words, it's just like, well, okay, I should not say that, but in other words, this work is equivalent to the initial heat taken up from the reservoir. So that then will give you eta equals to 1. But however, in nature, and in fact, because of the second law, in fact, you cannot have such an engine. Okay? So the most efficient engine that you can have, generally, okay, first of all, your Carnot engine is just a subset of a much more general heat engine. So in Carnot engine, the processes are reversible. Okay. So the general heat engine might involve irreversible processes. Okay. So in other words, what's the best engine that we can actually have is essentially the Carnot engine. I think somewhere along the line, which I have not made notes on, you actually have a theorem that says that, okay, the most efficient engine that you can have that obeys the second law is coming from a Carnot engine. Okay. So here's a symbolic diagram. So in other words, what do you have over here? You think of a heat engine taking here's a heat reservoir here. Oh dear. Something wrong with my just do this again. Okay. So it goes from some what's the cursor? It doesn't work. So it takes, so here's a, okay, I gave up. Okay, so it takes from a reservoir on top, okay, it takes energy from top of Q1, and your engine, somehow take part of those heat energy coming in from your reservoir, convert it to some work, okay? But then the second law requires forbids you to have total conversion of your heat energy from there to work. So there will be an excess heat energy for which you dump it into a different reservoir. So you get this kind of picture. So later on we'll compose different engines together. So we'll talk about that probably in the next lecture, because this is probably part of. Again, I'm having problem with my page over here. It's not going down. So as I said, Carnot Engine comes with reversible processes. In fact, the whole thing can be reversed. So I can invert this picture backwards. Okay. So I can invert this picture backwards. So instead of here, so releasing heat energy, okay, I'll take what you call, I take up Q2 from the reservoir and then release it back to the other reservoir, which is hotter here, okay, of the amount of Q1. So I can sort of change the direction of this heat engine, okay, and it's possible to do that, and this is precisely the idea of refrigerator. So you take heat from the cold body, okay, do some work with it and release it to a hotter environment. Okay, so I think that's about it. My notes finishes at that point. Let me just see if there's anything more here. I've not finished my notes for today's lecture. Well, I mean, there are more things to say about the heat engine, which we'll talk about it at the next lecture. Okay, I will take now. Are there any questions at this stage? Are you still there? Okay. So so I will take your attendance at this point. Oh, that's not what I want to do. Okay, I think that's it for today. I think hopefully I'll finish off this chapter 2 in the next lecture. Okay. So thank you everyone. Yeah, and now.